So we're looking at 2.3, and all of this has to do with continuity. So continuity means does the function not skip? Kind of like the joke about the coyote walking along and all of a sudden there's a hole. That's not continuous, right? So we're going to talk about that in a couple of functions as examples, which I think will be very clear. So one example, or one theorem, or the way the theorem 3 works. So theorem 3 states that if a function f is a polynomial function or a rational function with a non-zero denominator. At x equals c, then we say the limit as x approaches c of f of x is equal to c of x. And thus, it is continuous at x equals c. I have an example for you of just that. So I'll give you a minute to catch up with the writing. The example I have for you is a function that's very simple. It's f of x is equal to x plus 2. And I'm looking at the function, so if I have an xy graph, there's f of x, here's y. If I'm looking at the limit of this function as x approaches 2, of the f of x, which is x plus 2. So if it's okay, I'll just do this. The value for this is 4, and therefore f of 2 is equal to 4. So basically, if I'm looking at x plus 2, I can look at this and just graph it using an xy plot of numbers. And this is an example of a continuous function. So I'll graph it in red. If I'm here and here, this is where I'm intersecting the graph. I know that this point right here, where x is 2, y is 4, should be on my graph. So just drawing it, you can see it's continuous because there's no reason for 2 not x equal to 2 not be a function. It actually gives you a value. So that is an example of continuous at x equals c. Now the next two examples are not continuous. So they're the counter. If you're ready, I'll scroll up. If not, you need a minute, let me know. I am recording this. Are you ready for the other one, or you still need a minute? Yeah? All right, so this is an example of not continuous. If I have, for example, a function g of x is equal to x squared minus 4, and that is over x minus 2, do you notice that at x equals 2, what happens? You get a 0. So this is a discontinuous or not continuous. And so if you look at the picture that I'm about to draw, you'll see, again, here's your x and y plane. So here's x, here's y. And again, I'm still going to go through 2 at some point. But when x is equal to 2, what you will notice is I will have an open circle here, and it'll continue otherwise. So discontinuous. Coyote falling in the hole. We state this as the limit of g of x equal to 4 as g of 2, so x is approaching 2, where x is equal to 2 is not defined. So that's discontinuous. I have another example I want to show you where this does not exist. So give you a minute just to write that down. When you're ready, give me a heads up, thumbs up.
What do you mean by x equals c?
This is c. That's your c term. So when x actually, you notice I'm talking here about x equals c, so x equals 2. I'm not approaching from the right or from the left. I'm simply at number 2. So g of 2 is not defined, because if I substitute in 2 squared minus 4 over 2 minus 2, notice that I get an indeterminate function. So I would have to factor it. So there is a hole. And that's what we say is not defined. So imagine, let's just stop and just talk for a minute. Imagine if I took that x squared minus 4 and factored it, which would make it x minus 2, x plus 2. And this is over x minus 2. Right? If I factor that out, technically I'm left with x plus 2. And if I substitute in the value of 2 plus 2, should that not equal 4? Right? So when we talk about c, this is the c term right here. Are we clear? Yeah. And so remember, you can either approach that from the left or from the right. I've shown you charts where we're coming this way versus this way. And last week, Monday, I was talking about I'm touching you, that little game. It's kind of like the same game this is playing. Right? All right. I have one that is the next one. This is a really good example of does not exist, which we've talked about already. A third example. This is one that is not continuous at c, and we talked about it. This one is the absolute value of x over x. Do you remember that? Which, yeah, when we draw this on a graph, so this is your x, this is your y-axis. Basically, at 1, that's a hole going this way, and at -1, you've got another hole going this way. -1, +1. So we say in this case that the limit as x approaches 0, h of x itself does not exist. H of 0, we would say in this case is not defined. Okay, so let's wrap continuity up in one big little subset of possibilities. So by default, the book defines continuity. So this is a definition. Of continuity. Okay, so it says a function is function f is continuous at the point where x equals c if. Now there's three conditions that I'm going to share with you. Number one, condition number one, we either have the limit of x approaching c of f of x of whatever the function is, it actually just simply exists. The second condition they offer as an explanation is f of c exists. And the third condition that they state where this is true is as the limit of x approaching c given f of x is equal to f of c. Okay, so there's more to this, and it says a function is continuous on the open interval and then they give you open interval a comma b if it is continuous at each point on the interval. So I'm going to show you 4 examples that are going to help you master this definition. So let's draw a picture together. And I need you to be accurate, so I'm going to give you or call out specific coordinates. Are we done copying? Yeah. Okay. So let's draw our graph as such. If you would, preferably you do a better job than I do here. So there's x, and this would be your f of x. And obviously this continues on this side. This is negative x. All right. Let me use the book in this case. Okay. So at -4, 2. So 1, 2, 3, 4, 5. This is -5, -4, -3, -2, -1. On the right hand side, same thing. We're going to count 1, 2, 3, 4, 5. And going back up, we're going to also have 5. So 1, 2, 3, 4, 5. All right. So at the point -4, 2. So if you think about it, we're going to sort of do this and open circle. And we are going to go through the point going this way, the point -5. So this little point here is -5, 1. And this point here is obviously -4, 2. we're going to skip up a jump, and we're going to have a solid point at -4, 3. So this is 3, it's -4, so up here, sort of lining this up a little bit, you'll have a solid point, and then we go back up here to 5, and then we want 5, -2, which is about here. We have an open dot here, so this goes like this, and this crosses at 1, 4, it's an open circle. So it does that. At 1, 1, we have an open circle, and at 1, 2, 3, at 3, 3, we have another open circle, and then this shoots off in this direction as such. This picture is in your book on page 120 if you don't happen to have your book. And then at 3, 1, we have a solid line, or solid dot. This is 3, 1. This point here is 3, 3. This point here is 1, 1. This point here is 1, 4. And this point obviously is -2, 5. And this point here is, this one is -4, 3. -4, 3. Okay, so let me erase some of this little dashes that I have here. If you saw it in the book, it probably would be a little easier for you. I think this is pretty decent. And now we can discuss this. So given this diagram, we're going to look first at x equal to -4 and determine what is happening there. Okay, so we're going to look at number 1, where I'm saying here the limit. Let's discuss the limit as x approaches -4 from the left for f of x equal to 2. So you can see as we approach, I'm going to see if I can do this in yellow. As I'm approaching that value, -4, look, can you see the yellow highlight?
Yeah.
Do you see that this is 2?
Yes.
That's what they're referring to. We're approaching, so as x approaches -4 from the left, actually I came from the right, didn't I? Hang on. We're actually going this way. We're coming from the left. From the left, I'm approaching the y value that is equivalent to 2. Does that make sense?
Yes.
All right, cool. If I look at the limit on the second note, if I look at the limit as x approaches, what is wrong with me? Okay, so the limit as x approaches -4 from the right, what's happening there? I'm approaching from the right, so I'm coming this way. What am I going to hit? I'm trying to reach -4. So if you look at it, I'm here actually. So I'm approaching too far over. I could look at it as just simply coming from the right this way. I'm going to hit the 3 first. So we would say in this case, we'd say f of x is equal to 3 for that one, right?
Yes.
All right. If we actually look at the limit at x is -4, just the actual value, do you notice that these are not the same? Because that's solid, that's not. And so we would say as the limit as x approaches -4, in this case, does not exist. Interestingly enough. We do know that f of the actual value -4 is equal to 3, and we know that because of this. Does that make sense?
So when you said, when it does not exist, that's when you're approaching from the left?
No, it just doesn't exist
Oh.
because you notice how there's a jump?
Yeah.
Think of a bridge. Like the Key West Bridge, you guys know where the Key West, it's
Yeah.
broken off and it's like there's a jump, yeah, same thing.
And the 7 Mile Bridge?
There's a break. Okay, so we're gonna use this diagram yet again, but we're gonna look at -2. Okay, so I'm gonna erase this real quickly. And yes, I'm taking my time on this because I want to make sure that you catch the language as you, because math is nothing but a language, and calculus is its own little beast. All right, so let's take a look at -2, x equals -2. So the first one is this one here. We're going to look at the limit as x approaches -2 from the left. So we're coming to -2 from the left. Okay, so if I'm coming up to -2 from the left, what is my y value? 5. So we're at 5 here. For that one, x equals 5. The limit for the second one is the limit of -2, but we're approaching from the right. Again, if I'm approaching from the right and I'm looking to reach right here at -2, again, my value for y is equal to, f of x is equal to 5, no change. Now, for the same token, if I'm looking at f of -2, just -2, does it exist? No. So f of -2 does not exist. Because it's obviously empty, it's a hollow, right? Okay. Are you okay with that? Do you want 2 more examples or tell me? Do more? I'm gonna do 2 more. I got 2 more. All right, let's take a peek. See, gonna erase there. We're gonna erase there. Erase there. All right, let's take a look at in red. Let's take a look at where x is 1. So in this case, the limit as x approaches 1 from the left. What's happening?
You would hit -5.
What are we approaching? We're approaching 1, the number 1 from the left. So that means I'm coming this way. What do you think is going to happen?
4.
I'm thinking it's 4, yeah. So I'm coming this way. So it's got to be 4.
Why
So
isn't it 5? Like, maybe.
because I'm trying to get here. Let me draw the line.
Oh,
I'm trying to get here. Does that make sense? Because I'm trying to get as close to that 1 as possible, as in the red line I just drew. The 4 is definitely closer. Did that?
Yeah, that's what confuses me.
It is. It can be. Yeah.
Like, I don't understand why it doesn't hit the 1-1. Like, why it has to be the 1-4.
wait. It's because the line is coming from the left side and it goes closest to the 0.99999. But from the point at 1, 4. However, at 1.1, 1
Comes from the right.
1. 1.00 something something.
Right, and you'll see that here as I do the next one, which is the limit as we approach 1 from the right. And that goes back to what we're saying here. If I'm approaching from the right, let me do it in yellow, I'm coming this way, aren't I?
Right.
So what am I gonna hit? I'm gonna come here. My value should be 1. So this is 1.
Okay.
So it's what he's saying is correct. I just let him interject. Now, here's the question, the big question. When it's just 1, when it's approaching 1, does not exist. When the limit, when we have f of 1, does not exist either. Cool.
Can you make an example when it's not defined?
This one doesn't fit in that. So it's just does not exist. It's a 0. Hollow. We're gonna do a few more. Maybe we'll hit a couple more. I could do this continuity with 3. You wanna try f of 3? One last example?
Yeah.
Let me erase the red. Okay, so we're gonna look at at 3. So as x approaches 3 from the left, pay attention to the direction. If I'm approaching 3 from the left, just number 3, where is 3 from the left? Let me erase here.
3.
Hmm?
Isn't it 3?
It's just 3. It's just 3. So I'm approaching this value, this line, going up, going up. Okay, so I'm coming from the left. The first thing I'm going to hit is the y value of 3. If I say to you from the right, if I say the limit as x approaches 3 from the right, this also will be 3. So I'm coming again from this way up over.
Why isn't it 1?
Why isn't it 1?
Because of the graph line.
Because this is the limit at x is 3. At x is 3, then we would say f of x. I'm sorry. F of 3 is 1. That's when we say it's 1. If I look at the limit of x as x approaches 3, it's still 3. That goes back to that chart where you start putting in numbers. You start with 1.01, 1.02, and so on. Or you start with 0.9, 0.009, or 0.99, 0.999, and so on. And you'll see the differences in the values as you come closer, they'll start to pop in accordingly. But you have to be careful, especially here, and not confuse this topic. But that's specifically where f is 3 itself. That has to be 1. So again, that's language, that's notation, that's you taking in that definition. Can you start a sign-in sheet, one of you guys? Who's willing? Sign-in sheet. Who's willing? You willing? Awesome. Okay.
I still don't understand the explanation.
Of which one?
Just like why it's the top one and not the bottom one. Like 3-3 instead of 3-1. Is it because of the line? Like that's slanted upward?
No, the best explanation I can tell you is that as you come closer on integers. So if I'm looking at the value of 3, like 2.99999, for example, something like that plugged into an equation would still yield you a value. So again, you have to go back to math for this. plug in a value, I will get close to 3 as an answer as opposed to 1.
Okay.
When you have two close, 2 points that are close, instead of one open and then one close,
Mm-hmm.
that still is DNA.
D&E. That was this one right here.
That's because I think you're gonna have 2 points in the x value, right?
Right. Like in the example of when I did the limit as x approaches -4, that value does not exist. Let me see if I can find other information. I've got to stick to the schedule. But if I find other information, I'll throw it your way to see if maybe that example will help you. I'll put it in as a little video. So I don't stop working just because we don't have class. I promise you. Okay, let's talk about example 2. There's only 5 examples in this book, by the way, in this chapter. So example 2, we're looking at continuity of functions defined by equations, and I'm going to give you 3 really solid examples, as I always do. And so in example A, I have a function f of x, which is simply x plus 2. And we want to check at x equals 2. So in this case, f, and this might actually answer your question. Listen carefully to what I'll explain here for this one. F is considered continuous at x equals c, in this case x equals 2, because the limit as x approaches 2 for the function is equal to 4, which is also the same as f of c, which is f of 2. So you have to go back to those conditions I talked about earlier. Now, example B is not continuous. You're going to see how and why. Let's see if it hits you. We'll call this B. We'll call this g of x is equal to x squared minus 4 over x minus 2. And we're going to check it for continuity at x equals 2. And we would conclude that g is not continuous. Keyword not. Continuous. And you can tell already just by the denominator and because you have to factor. And again, that goes back to indeterminate. So we would say this is at x is 2, because 2 is the value we're looking, because or since g of 2 is indeterminate. It's 0 over 0. I proved that to you earlier. Do you remember when we plugged in the 2? We got 2 squared minus 4, which is 0. And 2 minus 2 is 0. So it's indeterminate. And therefore, we would have to factor it. We consider this not defined. Okay, so that's that one. I have a third example I'll share with you, which we talked about earlier, which is the function h of x, which is equal to the absolute value of x over x. We're going to check it at 0, and we're going to check it at 1. So we're going to use 2 values. So in this case, you could tell this is also not continuous. So we would say h, the function h is not continuous. At x equals 0. Right, because 0 over 0 makes it indeterminate, right? So, so we know that 0 over 0 is not defined. Also, we're going to check it at looking at the limit as x approaches 0 for the function. For the function, it does not exist in this case. Does not exist, right? Because I have a 0 denominator, it's no good. Undefined. So undefined and do not exist kind of go hand in hand, right? Okay, and if we check it at 1, we could say h is continuous. At 1, at x equals 1, because the limit as x approaches 1 gives us the absolute value of 1 over 1, which is equal to 1, which is also equivalent to h of 1. Is it starting to marinate a little bit? Yeah? Parts go in, parts do not. Let's see what else I had in the
Is that
notes.
I or 1?
That's a 1. Let me pass this page.
Did everyone sign this?
Yeah.
Alright. Okay, so I'm gonna hop over to number.
I left it with it.
Did I do this already? This is what I just did. Okay. I do want to bring some information to you, so you're gonna have to bear with me because I'm gonna rattle off a couple of properties of theorem 1. So we're gonna talk about theorem 1. There are A through F properties. And then we'll do some examples following. This is on page 122, 123. These are continuous properties of specific functions. So we'll start with A. Remember, this is A through F, how it's listed. So if I start with A, it talks about constants. You know what a constant is, right? Just like a basic number, no x, no variable involved, right? So a constant function f of x equal to k, where k is a constant. For an example of this would be if I have f of x is equal to 7, then it is continuous. This is important to remember. Is continuous for all x. This is not an x, this is a k. Would help if I write that correctly. So basically, f of x is y. If I tell you that y equals 7, isn't that a horizontal line all the way across?
Yeah.
And that's why we say it's continuous, because there's no interruption. Do you want to see the picture? It helps to see a picture, so I'll do a picture. So let's say hypothetically y is 7 here. F of x equals 7 looks like this. Okay? And that's continuous. There's no So X, there's an X here, there's an X here, X here, X here, X, 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 X is your worst dating nightmare. Kidding. All X's are continuous, right? All right, so here's part B. Let's see if this helps you. This is another specific function. This is for n, a positive integer. So we say in that case that f of x is equal to x to the nth, and it is continuous for all x. Is continuous for all x. An example of this would be if I have f of x is equal to x to the fifth. There is no interruption because it's odd, especially you have the positive, the negative, and it is continuous for all x. Right, because I can have, for example, negative 1 to the fifth. I could have positive 1 to the fifth. I still get an answer, right? So, okay. So that's part B. Part C. We have a polynomial. Function. Is continuous for all x, and they say in this case, for example, if I have a function that's like 2x cubed minus 3x squared, we have a plus x and a minus 5, is continuous for all x. Can you think of a number that I can't substitute in there? There's no denominator holding me back, right?
Yeah.
If I had a denominator, I'd have a problem. If I had a square root, I'd have a problem. If I had a radical, I'd have a limitation as well. Remember, that goes back to algebra. I always tell my students, think far. Fraction, absolute value, radical, you're going to have limitations. Okay, for D. Now this one you really need to pay attention to because this does have to do with a rational function, so you have a fraction. So a rational function is continuous for all x except those values that make the denominator zero. So they give you an example of a rational function. There's many more, but like x squared plus 1 over x minus 1. So we would say that this particular function is continuous except where x is positive 1. Does that make sense?
Yeah.
So you literally would have an answer of this is continuous. I'll just put CONT for all x except x equals 1 because it zeros the denominator. Right? Does that make sense? 1 minus 1, 0, bad. All right, another, am I going too fast? No, you're good. Okay, so part E. So for n, an odd positive integer greater than 1, we look at the nth value of f of x is continuous wherever f of x is continuous. So this takes a little bit of analysis. Is continuous wherever the actual function is continuous. So an example of that, because that sounds like gibberish to me until I saw the example, I was like, what are they talking about? So we're looking at the cube root, for example, of like x squared. The cube root of x squared, and we would say is continuous. For all x. Okay, and notice that they're focusing on positive integers also. Okay, for the last one, f. For n, an even positive integer say they give you the nth root again of f of x, nth root. We say that this is continuous wherever f of x is continuous and non-negative. So an example of this would be, say I have the fourth root of the square root of x. We would say this is continuous on the interval where I have 0 inclusive, comma, positive infinity. So let's do some examples that'll help us with this and understand this. All right, so this is on page 122, 123. If you want to go back and take a look at the notes, it might help you. This is also recorded, so all right. So that this takes us to example 3, where we are using continuity properties. So an example, let's look at example A. I'll do the example and the solution. In example A, they're giving me a polynomial function, which is f of x is equal to x squared minus 2x plus 1. So continuous for all x. So we would say since f is a polynomial function, therefore f is continuous for all x. So for example, if I were to graph this on Desmos, would there be anything disrupting this? You didn't see any hole or any number I couldn't? Absolutely not. There's nothing blocking this this polynomial. For b, I'll give you example b. So example b, we have x over x minus 2 and x minus 3. So obviously we have two zeros here. So we would say it's continuous except, so it's continuous except at x equals -2 and x equals 3. And we know that because the denominator can possibly become 0 at that point, right? What?
Shouldn't be x equal positive 2 because it's x.
+2, +3. Yeah, +2, +3. You know why I wrote that? Because technically the example was x plus 2, x minus 3. So I was, this would be negative. My mistake. Okay, you're really gonna understand the example E when they talked about part E, because in part E, which technically we're looking at C, this one is the f of x is equal to the cube root of x squared minus 4. So in this one, this is continuous for all x, and we know that because we're not restricted. Remember, cube roots can be positive numbers, they can be negative numbers. It's going to work out either way, right? So in our example, we would answer for this one, since it is a cube root, so we say n is 3, being that it is odd, right? So we have an odd root. The function is continuous. The function is continuous for all x. But what happens if it's even? Now we've got a problem, because we can never have the square root of a negative number. Right? You remember that?
Yeah.
Can never have the square root of a negative number. That's why part, or example F speaks of that. So in example D, we have f of x is equal to the square root of x minus 2. What do you know about this function? What would you say?
Continuous on the positive number.
Yeah, it has to be inclusive of 2, comma, infinity. So the numbers have to be 2 or greater for it to be continuous. So where x is greater than or equal to 2, since it's even, since the nth value is even, it's equal to 2, we say f is continuous for all values where x is greater than or equal to 2. Does that marinate?
Yeah.
Good. Okay. Theorem 2. Do you, by chance, was that example 3 by chance? Yeah. So we're on example 4, yay, we made it. Okay, so do you remember when you did the signs of it, what intervals worked in polynomial functions? You did that way back in algebra, where you had to draw like a number line and you put your zeros. So let's say you had 2 zeros, and then you would select test points.
Yeah.
Do you remember that?
Yeah.
We're gonna do that now, because that ties to this section. So this has to do with theorem 2. So we're basically going to apply that. So in example 4, so we'll call this example 4, we have solving an inequality So we have solve x plus 1 over x minus 2 greater than 0. That's all I'm asking you to solve. So what you're going to do is, if you notice, the numerator, if I say x plus 1 equal to 0, I get x equals negative 1. So that's one of my cutoffs. I call them cutoffs just for my own. X minus 2, if I do x minus 2 equal to 0, I get x equals 2. Notice that I'm using equals, not greater than, or less than, or, The reason for that is because these are my breakout points. So basically, I have negative infinity here, I have positive infinity here, I have negative 1, I have positive 2. Those are my cutoffs, gates, whatever you want to call them. They're my limits. I'm stopping there. Okay, and now I want to select a test point. So guess what? I am going to select 2, negative 2. I'm going to select 0, which I love using 0, and I'm going to select 3. And what we're going to do is we're going to pop this into the equation and see if it fulfills this standard. So in this question, for example, I'm going to take negative 2 plus 1 divided by negative 2 minus 2 and see if that happens to be greater than 0. If it's greater than 0, I'm really looking for what? Simply a positive result, right?
Yeah.
So if I do the math here, this is simply negative 1 over negative 4. The negatives cancel, leaving me positive 1/4, which is good. That's a positive. So that means that since I selected the negative 2, my interval is, this is a winner, right? If I put in 0 for the next one, the next test point, I'm going to use 0 plus 1 over 0 minus 2. Is that greater than 0? And you'll notice that you get a negative 1/2. Negative 1/2 is a negative and therefore not fulfilling what I'm looking for, right? So this interval, goodbye. Does that make sense?
Yeah.
All right. And the last one, since I'm running out of space, let's do it here, if you could still see. I'm going to do 3 plus 1 over 3 minus 2. Is that greater than 0? Well, this gives me 4 over 1, which is 4. We're good. So this interval is good. All right, so that means that your two solution areas in this case, and you would argue for f of x greater than 0 is true for the interval where I have negative infinity, comma, negative 1, not inclusive, union 2, comma, infinity, not inclusive. Is that clear?
Yeah.
No? Oh. All right. Okay, that's example 4. Example 5 is an application question. We can do it or skip it, it's up to you. Yes or what? Yes, do it? Okay. Okay, I'm gonna read it out loud, so if you listen carefully, again, this is the last example, example 5. It has to do with positive profit. So positive profit is the key. It says a bakery estimates its annual profits. Do you want me to write this down?
Wait, so it's gonna be a workable?
You want me to write it
I can
down?
like simplify it.
Yeah, I could. Okay, so let's just do this here. A bakery. A bakery estimates its annual profits from the production and sale of X loaves of bread per year to be P of X dollars, where P of X is equal to 6x minus 0.001 x squared minus 5,000 for which values of X does, oh my lord, does the bakery make a profit selling bread? Okay, so if we use the process we just covered, given this, the first thing you'd want to think about is maybe let's get this to where we're removing the decimals. So if I take out the decimals, maybe we can work this equation out and factor it out. Do you think that would work for you?
Yeah.
All right. Do you want to try it on your own?
Sure.
Give it a shot. You can also factor out the negatives. Is that what you guys got? Remember, you're taking out 1,000. So actually you're increasing the middle term by 1,000, which means you have to do the same thing to the latter term. Now we factor this out, you end up with x squared minus 6,000 x. And then this becomes positive 1, 2, 3. So 1, 2, 3, 1, 2, 3. So this would be 5 million, right? So this is minus here. So all they did here was they switched the numbers around. So you have to sort of play with the numbers. So this is really negative 0.001 x squared. Right, we're going to make that by multiplying by negative 1,000, we're going to actually make that positive x squared. All right, and then you have the plus 6x in the middle, which again, if you're multiplying by 1,000, this is really 6,000, and instead of 5,000 here, you have minus, you're multiplying that 5,000 times 1,000, which gives you 5 million. So this is plus 5 million. So originally that's what you have. This is the same thing, just rearranged. Right?
Yeah.
Okay.
Would it be negative?
Negative 5. Yeah, I wrote the answer. I'm down by the answer. So it's negative 5,000. So we're multiplying all of this by 1,000.
Well, by minus 1,000, right?
No, minus 1,000. So you get a positive x squared here. Negative 1,000 times negative 0.001 x squared is 1x squared. Negative 1,000 times positive 6x leaves you with negative 6,000x. And negative 1,000 times negative 5,000 is positive 5 million. Now you just have to factor it. Go back to FOIL. 2 x's, so x and x. This is a positive, so this has to be a negative times a negative, so 2 negatives. And you know that because that's a negative. And then 2 numbers that multiply to give you 5 million. Take out the zeros. Just think of 2 numbers that give you a 5 as a multiple. 1 and 5. And they add up to 6, yeah. So in this case, that's why we put 1,000 here instead of, instead of the 1, and here 5,000 instead of the 5. Inner outer terms, there's 6,000. So that's how you know that your values are going to be x equals 1,000 and x equals 5,000. And those are your cutoffs. Remember I said cutoffs. Now in here, we selected a number. Let's select 2,000. Out here, we're selecting something less, and up here, we're selecting something a little higher. Let's say we chose 6,000 here. And let's say over here, technically I could choose 0. Keep my life simple. Right, just plug them in. You plug in the answer. You can literally just do the math straight up as it is. And so it turns out that the only values that work are right here, in here, from here to here. Because if you do 0, you get 2 negatives. The 0 gives you an answer of negative 5,000. If you used negative 10,000, you got negative 45,000. However, in the middle, let's say we chose 2,000 here. This actually would have worked, giving you a positive answer. Okay? All right, we are, I'm going to start opening up the quizzes. I'm going to start with section 2.1, 2.2, 2.3. Give you the weekend to do it. They're separate quizzes, okay?
Don't you mean a week? Because one has to go home.
Correct. You have the weekend. You have a 3-day weekend, so. Toodles! You too. Don't get carded.
Have a great week.
Don't get carded now.
I'll try not
All right.
Want to Wednesday? Want to Monday?
You're good.
Online.